I actually have several stories, and the first one has this really long title in the paper, but what it is it generated this picture, and this is a picture using a radio or a set of radio telescopes called ALMA, which stands for the Atacama Large Millimeter Array, and that's what this ring is showing. And it's also imagery from the Hubble Space Telescope. So that's what this kind of bluish blob is showing. And so these aren't the colors that you would see because what the astronomers have done is taken the radio imagery, obviously we can't see in the radio, but converted into this orangish red color. And I'm not sure what the Hubble Space Telescope image, what color light that is, but it might be bluish, and then combine them together. But basically, we are seeing something known as an Einstein ring, and this is entirely due to how we understand gravity via Einstein's general theory of relativity, that gravity can actually bend light. And so this bluish blob is actually a galaxy that's closer to us, and this red light is coming from a galaxy that's further away. And so that light, and these two galaxies are more or less aligned back to back, and so the light from this galaxy is being bent and distorted by the gravity of the foreground galaxy, and hence this is what we see by that distortion. So, as I said, the really high resolution imagery, you can see that there's much more detail here than you can see even with the Hubble Space Telescope, and that's because the ALMA telescopes is an interferometer, meaning there are lots of telescope dishes, radio telescope dishes, and when you spread them apart in space, meaning keep them separated, these are actually on pads, but you can move them around. But the further apart these telescopes are set, the more resolution, the higher the resolution, or the more detail that you can see. So that's how they can get images that are more detailed than the Hubble Space Telescope. But because this is in the radio, they're also observing different species of molecules. So in this case, we're looking at carbon monoxide, which is visible in this particular part of the radio spectrum. And there, as I said, this is an example of an Einstein ring, and there are other examples that that we can see, many in the sky. The following sets of pictures are from the Hubble Space Telescopes, and so these are images taken in the optical, so in visible light. So again, here is a foreground, large, massive foreground galaxy, and then there's a background galaxy that's probably a tiny fraction of the size of this ring, but because it just happens to be lined up just right, that light gets spread out. And in this case, this is more of a horseshoe shape because the two galaxies aren't aligned exactly, they're slightly off. But here is an example of a bunch of Einstein rings that are pretty, most of these are very close, especially this one and this one to being exactly in line. So what you can do based on this type of imagery is to actually figure out roughly exactly how far the foreground and the background galaxies are. And so in this case, the light from the foreground galaxy, the Hubble image, took about 3.5 billion light years to travel to us. So the light that we're seeing shows what this galaxy looked like 3.5 billion years ago. And then the further galaxy, the one that we see as this red ring, that light left the galaxy about 11.5 billion years ago. So these two galaxies, the light we're seeing, are separated by about 8 billion years. And remember, the age of the universe is 13.7 billion years. And so this background galaxy is very close to the beginning of the universe. The other thing you can do is you can actually create a computer model that extracts out what the what that background galaxy actually looks like. So this is what they determined as to be the actual, if the foreground galaxy wasn't there and distorting the light from this background galaxy, this is what that galaxy would look like. But because it's being distorted by this gravitational lens from that foreground galaxy, this shape gets stretched out into that ring. And then so here is just a video showing what exactly is happening. And so here is the foreground galaxy without the gravitational lens. And then if you were to move the foreground galaxy, you can see it gradually get distorted until you get this ring here, and then also a partial ring on this side. And that's just because the two aren't exactly aligned. And then the other thing that they were able to discover, and we just saw that in the subtitle, is that they were able to identify not only a main mass due to the foreground galaxy, but they also found a dwarf galaxy located roughly about here where this bright spot is, because they were able to find additional distortions in the structure or in the substructure of the ring that couldn't be completely explained by just having one mass. So if you have two masses, so this main mass is about 400 billion solar masses, so that's about twice the mass of our own Milky Way galaxy. But if you assume that there's also a smaller dwarf galaxy that's just under 1 billion solar masses, then you can actually explain some of the weird substructure that you find. So this is kind of an amazing technique, because not only are you using this gravitational lens from that foreground galaxy to blow up and to magnify the light from that background galaxy, even though it gets distorted, you can, through computers, basically figure out what that shape of that galaxy is without the distortion. But you can even determine and find smaller foreground masses. So this dwarf galaxy is 1/400th the mass of the main galaxy, and we're able to detect it, even though, if you remember the previous images, there's nothing that shows up in the Hubble image to suggest that there's anything there. So here is a way of using Einstein's theory to give us a lot more information about both the foreground and the background object. Now my next story is also related to Einstein,